Okay, thank you. So finally, this is the last class of this course, and then on Wednesday we will take the final exam of this course. So in the previous class, I conclude the memory hierarchy part. So I said that this memory hierarchy part is the important topic in the computer architecture course. So actually, I emphasized that the instruction set architecture and process architecture and then memory hierarchy is the most important 3 topics in this course. Okay, and then so this is the last regular class. In this class, I will briefly introduce about the parallel processor. Okay, so recently the most of CPU is the multi-core CPU. So which means that in a single chip, there are multiple cores. Then what is the core? What is the core when we mention multi-core architecture or multi-core CPUs? So for example, the Intel i7 have, I believe it's about the 4 cores, maybe. So recently, the Intel also increased the number of cores in their chip. So I think the number of cores of i7 is about the 4 or 6, maybe. Then what is the core? Core, okay. So core is so you can think that core is independent processor, which include the cache, okay? So core means the independent. So which means that our processes, so which means our thread can be executed in this core independently. So this is the independent processor. So in chapter 4, we learned about the architecture of the processor. So which means that this individual core includes the completed processor design, which include the instruction fetch, the instruction decoding or execution, memory part. So which means that this core also includes the level on cache and the level to cache. And then also the processor has the write back part. Okay, so core means the independent process, and then also when we mention a core, this core includes the level on caches. So level on instruction cache and then data cache. Also, most of core includes the level 2 cache. So which means that we call these caches are private cache. Okay, but in a multi-core architecture, there are multiple cores. So and then each core includes until level 2 cache. But in a multi-core architecture, there are level 3 caches. So this is the last level cache, and then this level 3 cache is shared by multiple cores. So the most of modern processors are multi-core processors. Okay, so in this chapter 6, so we will learn how these parallel processors are designed, and also we will learn about the basic concept of the parallel processor architecture. Okay. So this is the goal of this chapter. This is chapter 6 of this course. So we will learn about the multi-core architecture. So these architectures are called the multiprocessor architectures. And then in this multi-core architecture, these are important topics. So what are these topics? So it's the scalability, availability, and then power efficiency. So scalability means that, so if we use the multi-core architecture, then there are multiple cores, then we expect that with this multiple cores, we can increase the throughput. So its throughput is also performance. So we can increase the performance. So which is proportional to the number of cores. So which means that if we buy dual core CPUs, then we expect that the performance can be improved by twice, 2 times. Okay, but it's not possible actually. So also it's, so you can think like some real world example. So for example, so think like this case. So this is the group project, but it's so you can work as an individual. So which means that so we can include the one person per group. Also, so we can also design the some, how can I say, some two persons per group. Okay, but we cannot say this group exhibit the doubled performance compared to this, how can group configuration, right? Okay, why this the multiple? So what's the reason? So which means that so why the performance of the multiple students per group is not it can be better, but it's not proportional to the number of people or number of students, because there are overhead. Also, the another reason is that our task includes some parts that cannot be parallelized, right? So some tasks should be serialized. So which means that the tasks, so this task includes, some project includes the multiple tasks, like the task 1 and task 2 or task 3. But some tasks cannot be parallelized. So which means that the workload included in this task cannot be divided. So in this case, so 2 persons per group is not efficient, right? So another overhead is the communication overhead. So which means that even though two persons are working for the same project, but so there are some overheads such as the communication overhead. So which means that the data should be communicated between these 2 persons also, and then this overhead should be considered. Okay, so also that's the same to the this multi-core architecture. So which means that even though multi-core includes the multiple cores, actually this is it's unfortunately, so the performance of this multi-core architecture is not proportional to the number of cores. So this issue is called the scalability issues. Okay, and then availability means that also you can say that so when a task is assigned to a certain processor, and then this processor need to communicate with some other part of the processor, okay, so other part of the CPU chip. So, and then even though there are multiple cores, like some, for example, the input and output devices, so some parts, some component has the limited hardware resources, and then these processors need to use this limited hardware resources. So in this case, so this resource is if this resource is occupied by a certain core, then the other core cannot use these hardware resources. So this is called the availability issue. And then power efficiency. Power efficiency is a very critical topic in the modern processor system, modern processor architecture. So because the power is very critical. Okay, so this is the running cost of our computer systems. Also, in order to use this parallel processor architectures, then our task, as I mentioned, our task should be parallelized. So what does that mean? So think like some very simple mathematics algorithms, so think like some very simple code. Okay, so when you think about the code, then we write the code like a single thread code. So which means that when we design a code, then this code is executed from top of the code to the bottom of the code sequentially, right? That is our flow of idea, right? When we write a code. So actually, so when we think about some computer instructions, we assume that every instruction is sequentially executed from top to bottom, right? But in order to use the parallel processor architecture, so which means that this CPU chip includes multiple processors, so which means that these multiple processors can execute multiple threads. So which means our algorithm should implement the parallel algorithm. So like the A plus B plus C plus D, when we think about this very simple addition, then we first think that, oh, for this addition, the first performs this add, and then this add, and this add. So it's a sequential algorithm. But when we think about the parallel algorithm, so we can split this addition to the two parts, like A plus B and C plus D. So one processor performs the A plus D, and then the other processor performs C plus D. Okay, and then these are added. So so this is a very simple example. So, okay, so we also need to implement the parallel algorithm to exploit the multi-core architecture. Okay. Okay, so this is some example of parallel processing hardware and then parallel processing software. So this is the example of the serial processor. So this means that a CPU chip includes only one core. Okay, so as you can see, this is the very old CPU. It's a Pentium 4. So originally, each CPU includes only one core, one individual core. Okay, and then we focus on increasing the performance of this single core, or in the okay, but recently we use multi-core CPUs like this parallel hardware. So with this parallel hardware, this single CPU chip, there are multiple cores, like the quad core. This is the example of the Xeon processor, but this is the number of cores is just 4. But recently, the modern Xeon processors includes about the 20 to 30 cores. Okay, so which means that the tens of cores can be included in the Intel Xeon processor. So which means that actually the modern computer systems rely on the multi-core architecture. So, and then with this multi-core architecture, that we can execute multiple number of threads concurrently. Okay, and then think about the software. So usually we write a code. So write the code, and then this code generates the single thread. So what does that mean? So when we execute some very simple code like the hello world, this is the first code which can be written in C. then this code is the single-threaded code. So it means that when the code is executed, then this code generates only single thread. Also, and then we implement the most of algorithm with the single-threaded program. Okay, so which means that the single thread is generated, and then this single thread is executed serially. So serially means that from top to bottom. And then think about the operating systems, like the Windows or Linux operating systems. So when the operating system is launched and executed, these operating systems generate multiple threads. And then when the multiple threads are generated, then these multiple threads can be executed on multiple number of cores concurrently. So which means independently executed. Also, the most of modern applications such as the web browsers, so also these modern applications generate the multiple threads. And then so we can also design software for parallel processors. Okay, but challenges that, and then these are some commercial, so and then like some very simple general purpose applications. But if we just focus on the scientific applications or some if we just also, for example, if we focus on the neural network applications or AI applications, then this parallel algorithm is very, very critical. So which means that, so I mentioned that when we design a code, then most of the algorithm is a serial algorithm. Okay, so because this is very natural. Okay, we assume that our code is executed from top to bottom sequentially. So this is our assumption, but parallel algorithm is different. So which means that when the parallel algorithm is designed, then this algorithm generates the multiple thread. So which means that the data is splitted. Also, this split data can be processed by multiple threads. Okay, so we need to design this parallel algorithm. We need to design these parallel algorithms. So, okay, so designing parallel algorithm, so making effective use of parallel hardware. So designing parallel algorithm is very critical for exploring multi-core architecture. Okay, so I also, so as I mentioned, so this is the parallel programming, and then actually this is the out of topic of in this course. So I think the parallel, I forgot the course, the name of the course, but I believe some graduate course. So the graduate, so if you take some advanced course in this department, like then you can learn how to use OpenMP or pthread. So actually, we can generate the multiple thread using this OpenMP or pthread libraries. So which means that so we can split our data used by our code, and then we can also generate some independent thread that process this split data. So I said that we need to divide the data which are processed by our programs. So partitioning is also very important. So we need to partition our data. Also coordination. So if the data can be independently executed by multiple threads, then partitioning may be easy. But if we just focused on some algorithm like the matrix multiplication. So which means that think like the matrix multiplication. In order to perform the matrix multiplication, then we need to perform the vector multiplication for the row of this matrix and then column of this matrix. Okay. So, and then after that, the result of these vector multiplications, which are called the partial sum. So these partial sums need to be accumulated, right? So which means that the data should be also accumulated with the data computed by multiple cores. So this is the coordination. Also, we need to also think about the communication overhead. So which means that the data should be delivered to the other cores, or also data should be a certain core need to receive some data from other cores. So this is the communications. Okay. Okay, so these are overhead of parallel programs. And then let's think about the Amdahl's law. So Amdahl's law is actually very popular law, and then actually this law is not difficult. So actually this law is very obvious. Okay, then what is the Amdahl's law? So Amdahl's law means that so we can split our workload. So which means there's some data. So we can split our workload to the some workload that can be enhanced and some workload which cannot be enhanced. Okay, right, it's obvious. So if we just add new architectural ideas, but these architectural ideas cannot improve every part of our data or every part of our workload, right? We cannot improve everything. So we can divide our workload into the two parts, which can be enhanced and then which cannot be enhanced. And then by our new idea, only this part can be improved. So if this is improved, then we can reduce the execution time of this part by some n, and then this is not changed. Okay. Okay. So this is actually Amdahl's law, and then Amdahl's law says that actually the overall performance, the limitation of the overall performance improvement is restricted by this part, right? And then this Amdahl's law can be also applied to parallel architecture. Okay, so let's think about the Amdahl's law in the parallel architecture. So Amdahl's, when I mention Amdahl's law, so I said that we can split our workload into the workload, which means the workload which can be improved, and then the workload which cannot be improved. So which means if we apply Amdahl's law to the parallel architecture, so we can, which means that we can split our workload into the workload which can be parallelized and workload which cannot be parallelized, right? Like this is the serial part. And then if we apply multi-core architecture, and then the execution time of this parallelizable part can be reduced by n if we apply n-core multi-core architecture, n-core architecture. right? So there are n cores, and then we can reduce the execution time of this parallelizable part by divided by n, right? So which means that this is the enhanced the execution time of the workload by multi-core architecture. Okay. So this is the example. So let us assume that a single CPU includes 100 cores, right? And then actually T original. So this is the execution time of the original workload can be split into the T parallelizable part plus T serial part, so sequential part. And then with the multi-core architecture, we can improve the only this part by 100. Okay, so this is the T parallelizable part is divided by 100, and then T sequential is not changed. It's not changed, right? So this is the new execution time by 100 processor. And then how can we get 90 times of speed up with the 100 processors? So you may think that, and then we need to calculate this part, the fraction of the parallelizable part. But you may think that, there are 100 processors, and then, we want to get the 90 times of speed up. With the 100 of processors, then we can think that, we can easily reach the 90 times of speed up. Why? Because we think that the performance is proportional to the number of cores, right? But by Amdahl's law, in order to gain 90 times of speed up, then the fraction of parallelizable part is the 0.999, which is the 99.9% of workload should be parallelizable. Okay, so which means that the most of part, about 100% of the workload should be parallelizable, right? But this is obvious. See, this is the simple equation, and then based on this simple equation, then we can say that, because of this part, then this limitation, the performance is restricted by this parallel architecture, right? So think like also this example. So let us assume that this is the workload, and then this workload is composed of sum of 10 scalar, so which is it's a sequential part, and then 10 by 10 matrix sum. Okay, so I believe everyone knows how to sum two matrices, right? So we can implement the parallel addition for this 10 by 10 matrix sum. Okay, and then let's compare the speed up by 10 processors and 100 processors. For the single processor, the execution time is 10 scalar addition and then 100. So each matrix has 100 elements because we are adding 10 by 10 matrix. So this is the execution time of single processor. So T add. And then if we apply the 10 processors, then we can reduce this part, right, by 10. So this is the new execution time, and then execution time becomes the 20T, the T add. And then what is the speed up? Speed up is the 110 divided by 20 is the 5.5. So which means that even though we invest 10 cores, and then for this workload, the speed up is about the 5.5. It's the 55% of potential. So potential means that we assume that with the 10 cores, we can get 10 times of speed up. But actually, for this workload, this part cannot be parallelized. So speed up is just 5.5. How about the 100 processor? So very simple. And then the total execution time becomes 11T. So it's the speed up is about the 10. Just 10, even though we invest 100 cores. Okay. So what's the problem? Because of this part, we cannot get peak performance. The peak performance is proportional to the number of cores, but we cannot reach that point. Okay. But if we increase, so if the problem size is fixed, the Amdahl's law is very pessimistic. So which means that we cannot get this peak performance. Okay. But if we can increase the problem size, so which means that we can increase the parallelizable part. So which means that we can apply the 100 by 100 matrix, right? So for the single processor, this is the execution time, and the 10 processor is we can reduce this part. Oh, the speed up is about the 9.9, so which is very similar to the 10, right? So what does that mean? If the problem size, so which means that the fraction of parallelizable part is fixed, then with the Amdahl's law, it's very pessimistic, so we cannot reach the peak performance. But if we can apply the multi-core architecture, so which means that, then we can develop the new software, so new application, so which have large fraction of parallelizable part. Right, that can be possible. So in this example, we increase the size of matrix, right? And then as we use the big matrices, then the performance becomes very similar to the 10, right? Also, 100 processor performance speed up becomes 91. Okay, so compared to this result, and then if we apply the multi-core architecture, then and if the problem size is increased, then the performance can be also increased. Potential. So potential is the same to the number of cores. So as I mentioned, so if we use the 10 cores, then our expectation, the peak performance is that its speed up is 10, right? Because there are 10 cores, and then every workload, every part of workload is parallelizable, then that is the peak performance. Understand? So potential is a 10 for the 10 processors, and then this is the 100 for the 100 processors, right? Okay. So this is the some scaling problem. So actually, if the problem size, as I mentioned, the problem size is fixed, then Amdahl's law says that the part which cannot be improved, decides the performance, the limitation of the performance improvement. Okay, so this is very pessimistic. But if we increase the problem size, then the performance is close to the peak performance. Okay, right? So then what does that mean? So actually the Amdahl's law says that the multi-core processor is not good, right? So actually every application includes the sequential part, and then with the multi-core architecture, we cannot improve the performance of this sequential part, right? So actually the performance improvement is limited by this sequential part of one application. But if we apply a multi-core architecture or multi-core processors, then this problem size, the problem size of software is changed. So what does that mean? Actually, so software engineers implement the new application which include the large fraction of parallelizable part, because this software need to exploit the benefit from multi-core architecture, right? So which means that the software is also changed. The problem size is changed. So we can enjoy so we can enjoy the benefit from the multi-core architecture. Okay, and then so actually this in the real world, so in the multi-core architecture, multi-core processor is firstly introduced, that most of application was the sequential application. So which means that even though we apply the multi-core architecture, then performance is not improved. But recently, the most of application generate the multiple thread. So as for example, the Google Chrome, the Google Chrome launches many thread when the Chrome is executed, right? So you can check the launched processes by Chrome by clicking the Ctrl-Alt-Del, and then check the launched processes on Windows. Okay. Also, you can check the launched processes using tab command on Linux operating system. Okay. So it means that the software is also changed to exploit the multi-core architecture. Okay. And then let's think about some relation between the multiple instructions, and then multiple data streams. And then, so this is the classification of the processor, and then this classification is called the Flynn's taxonomy. Okay, so taxonomy means in Korean 분류학, which means that it is a study related to classification, right? So actually the Flynn defines some different classes of processor based on the kind of instruction streams and then data streams. So which means that we can execute a single data using single instruction, or with a single instruction, we can the processor handles multiple data. Okay, or with the multiple instructions, these multiple instructions can handle a single data. Okay, so based on these single and multiple instruction streams, and then single and multiple data streams, then we can classify a processor into 4 different classes. Okay, so for the instruction, we can say that this is the single instruction or multiple instruction. And then for the data stream, we can say that this is the single data or multiple data. And then by combining this SI and then some multiple data, like data, then we can classify a processor into 4 groups, like SI-SD, SI-SD, and then SI multiple data, SIMD, and then multiple instruction and single data, MISD, and then multiple instruction and the multiple data, MIMD. Okay. So this is the very classical processor. So it's a single core processor. And then with a single core processor, then this processor can only can run single thread. Okay. And then actually we learn the very typical instructions, the RISC-V instructions. But if we just consider these instructions we learned in this course, then most of the instructions handle single data, right? Like add R1, R2, R3, or X1, X2, X3, okay? So these are called the SISD, it's a very classical uniprocessors, okay? And then SIMD, so with a single instruction, then multiple data can be processed by single instruction, which means that single instruction can handle vector type data. So like a vector type data. So actually, the most of commodity processors, the most of commercial processors includes the SIMD instructions. So which means that those processors include vector type instructions. Okay. For example, this is SSE instructions in x86 architecture. Also recently, the x86 architecture support AVX. So these are examples of vector type instructions and SIMD. So most of commercial processors support SIMD type instructions. Okay, because these kinds of data are frequently observed in multimedia applications. Okay, so that's why the SIMD is frequently used. And the MISD, this is very inefficient, so no examples today. So single instructions handle the multiple instructions handle a single data. So this is very inefficient. Okay, and the MIMD, this is the multi-core architecture. Okay. Okay, I said that vector processors is the example of SIMD processors. So which means that, so what is the vector instruction? Like vector add, so we can perform the V1 plus V2. And then, in this vector, there are multiple elements, right? And then when the vector add is performed, then multiple elements are added each other, right? So, which means that with a single instruction like vector add, then these multiple elements are processed. So this is the example of SIMD type processing. Okay. The RISC-V also supports the vector type instructions, and so like vector extensions of RISC-V. So RISC-V also supports these instructions. Also, in order to support the vector type instructions, the RISC-V also includes the vector type registers. Okay. So in these registers, so there are 32 registers, and then each registers can store 64 elements. So the register size is very large, right? But this is very efficient because with a single instruction, then multiple elements can be executed concurrently. Okay. So this is the example. Okay. So actually, the vector type instructions are widely used in the commercial processors. Okay. Okay. Then, and then I will briefly also, I also so this parallel processor topic is the so actually in this course we learned about the process architecture, so single core actually, also memory hierarchy, but the but parallel process architecture is the kind of some advanced topics in the computer architecture. Okay, so that's why I briefly introduced some concept of parallel processing. Okay, so I will also briefly introduce the hardware multi-threading. Then what is the hardware multi-threading? So this is the multi plus threading. So what is a single thread? So when the application is executed, then the thread is launched, and then actually a core execute this single thread. Okay, so single thread is assigned to a single core, and then this core execute single thread. That is the process model we learned in this course, right? It's a single thread. Then what is multi-threading? So like multi-threading. So as you can expect, multi-threading means that multiple threads can be executed. Okay, so which means that so these are multiple threads. The multiple threads can be executed by a single core. This is the multi-threading. Then how can it be possible? So multiple threads can be executed by a single core. So in order to execute a thread, actually in order to support the multiple thread, what is required? So in order to which means that so in order to execute thread, then what is required? When the thread is so think like this. So instruction. So this is the processor model. So instruction is given to a processor, then processor change the register file and memory. Okay, but so memory can be shared by multiple thread, right? So actually, computer systems, the same physical memory is shared by multiple applications, right? So we already learned the virtual memory systems, right? So same physical memory is shared by multiple applications. Memory is already shared. Now how about the register? So like this one. So add x1, x2, x3. When this instruction is executed, then actually the register file is occupied by this instruction. So it means that in order to support multiple thread, and then if a processor has first multiple registers, then we can execute multiple thread, right? Because when an instruction is executed, then the result of this instruction is stored in the register file, and then register file is managed by compiler. Okay. So actually, in a modern processor, the modern processors have enough number of processing units. Okay. Actually, there are many different type of instructions, like integer type instruction or floating point type instruction or special function instructions, and blah, blah, blah. And then in order to support these various types of instructions, actually a single core includes the many different type of execution units, like integer ALU, floating point ALU, or some square root ALU, blah, something like that. So there are multiple execution units. And then with these multiple execution units, then we can execute actually multiple instructions. So multi-threading means that if a processor have multiple register file sets, then actually in the instruction cache, we can fetch multiple instructions, right, for the multiple thread. And then these instructions are executed, and then if there are multiple registers, when the instruction is executed, then result of this instruction is stored in the multiple register file set. Okay, so this is a very fancy idea, right? So which means that if we just add more register files, so more register files for multiple thread, then we can implement multi-threading. This is the multi-threading idea. Also, this multi-threading idea is also very useful because when a thread is executed, and then if this thread encounter cache miss, right, then this thread need to wait until the data is fetched from the low-level cache or memory, right? And it will take a very long time. And then while this thread is waiting for the requested data, then the processor cannot do anything, right? Then a processor can change it to different thread, and then the processor can execute the instructions in different thread, right? So this multi-threading is also good for the cache miss event. Okay. So, okay, so this is very popular figure of that explains the hardware multi-threading. And there are three different kinds of multi-threading. So the first one is the coarse-grained multi-threading. So coarse-grained multi-threading. And then the second one is the fine-grained multi-threading. And then the last one is the simultaneous multi-threading. Okay, simultaneous multi-threading. And then actually this simultaneous multi-threading is the Intel hyper-threading. So, and then what is hyper-threading? So hyper-threading supports multiple logical cores on a single physical core. So if a hyper-threading is supported, it can run 2 threads per one physical core, right? One physical core. So which means that this hyper-threading actually implement the simultaneous multi-threading, okay, SMT, okay? Then what is different? So this is the instructions in a different thread, so thread A, thread B, and thread C, and thread D. And then when a processor supports hardware multi-threading, then I said that multiple threads can be executed in a single core, okay? So coarse-grained multi-threading means that when a cache miss is encountered, then this processor changes the executed thread. Okay, this is the coarse-grained multi-threading. So this is the example. So let us assume that thread A encounter cache miss at this point. So actually this thread cannot execute any instructions because of cache miss. So in the coarse-grained multi-threading, thread A is executed, and then cache miss is encountered. So then of this processor changes to thread B, and then thread B is executed, and then cache miss is encountered, then it changes to the thread C. This is the coarse-grained multi-threading. And then the fine-grained multi-threading, the thread is changed every cycle. Okay, the cycle 1, the thread A is selected, and cycle 2, and thread B is selected. Okay, and then simultaneous multi-threading instead, a CPU can execute any instructions, any possible instructions in multiple thread. Okay, so if you see this model, so simultaneous multi-threading model, then you can find that, oh, there are 4 slots, 4 instruction slots in this processor. And then as you can see, the simultaneous multi-threading, at the first cycle, 2 slots are occupied by these 2 instructions of the thread A, and then another 2 slots are occupied by 2 instructions of thread B. And then after 1 cycle, then this instruction is occupied, and then 3 instructions are of thread C are occupied, so assigned to the execution slots. Okay, this is the simultaneous multi-threading. So as you can see, the efficiency is higher if we implement the simultaneous multi-threading. Okay, so actually this simultaneous multi-threading is the hyper-threading in Intel CPU. Okay, so this is a very fancy idea because a CPU already have enough execution units that can execute multiple instructions. Also, so the thread may encounter cache misses, and when the cache misses are encountered, then we cannot find possible instructions in the thread. Okay, so in this case, and then by adding multiple register sets, then we can execute multiple threads in a single core. But disadvantage is that the core architecture, become more complex if we implement the hardware multi-threading. Okay, so sometimes we can, it can be more efficient if we implement the multi-thread using multiple very simple small cores. Okay, so it's the multi-threading. Then this, in order to implement this hardware multi-threading, then the control part of the core becomes more complex. So which means that the core size is increased, and then the core design is very complex. But in order to support executing multiple threads, then we can use many simple and small cores. Okay, so with these multiple simple and small cores, then we can also execute multiple threads. Okay, so this model can be more efficient if our applications can be parallelizable. Okay, actually this is the GPU's execution model. Okay, GPU supports the massive parallel processing, so which means that so if you see the specification of the NVIDIA GPU, then you can find that NVIDIA GPU includes the 100 cores, right? So like the 900 cores or even 10,000 cores. But think like Xeon. Xeon is a very expensive CPU, but Xeon includes 20 to 30 cores. But NVIDIA GPU includes the 1,000 cores. Is it possible? How can it be possible? Because GPU includes the very small and simple cores, but Xeon includes the very complex and big cores. Okay, so that's why Xeon includes the only 20 to 30 cores, but Xeon is also very expensive. GPUs are also very expensive recently, but GPU includes the lots of cores, lots of small cores. Okay, So this is the some GPU model. So actually, the GPU are designed for graphics application, but recently, as you know, the GPUs are widely used for parallel applications such as the neural networks, right? So GPUs are very expensive because of neural networks, also the cryptocurrency like Bitcoin. Okay, so like this is the GPU architecture. The GPU architecture actually includes the very simple cores like this. So in this figure, the GPU includes the SP, so it's a streaming processor, but this streaming processor is very similar to the integer and floating point ALU. Okay, so the structure is very simple, and then also the size is very small. But with this small cores, the lot of small cores, GPU supports the very efficient parallel processing. Okay, and then also the GPU structure, GPU architecture is very different from CPU architectures. Okay, and it is GPU, but so we will not learn about the GPU architectures or interconnections in this course because this is the advanced topics in the computer architectures. Okay, so I will conclude this chapter 6. So in the chapter 6, we learned about some parallel process architecture briefly. So we learned about the the Amdahl's law and how Amdahl's law can be applied to parallel process architecture. So we learned about some techniques such as the hardware multi-threading. So we learned about some Flynn's taxonomy, so vector type processors. But these are advanced topics. So if you are interested, then you can also take the advanced courses on computer architecture. Okay. Okay. So this is the last regular class. So how can I? I will conclude. I will close this course. Okay. So this was the goal of the discourse. So what is the goal of the discourse? So exploring computer system architecture at an abstraction level. So abstract level. So I cannot write. Okay. So it's an abstraction level. So we learned that computer systems are composed of many abstractions. Also, we learned some hardware part, and then hardware and software interfaces as an abstraction level. Oh, so I will also post the announcement about the final exam after this class. But the final exam will be taken placed in the same room, so same classroom, right? And then also I also post the final exam time, right? Okay, so I will post the announcement about the final exam on the Blackboard after this class. Okay, so these are what covered in this course as I introduced in the syllabus. So we learned about the performance metrics. So in the instruction set architecture, this is the chapter 2, and then chapter 3 we learned in chapter 3 we learned about the arithmetic logics, and then very simple hardware units for arithmetic computations. And then in chapter 4, this is the very critical part of this course. So we learned about the pipelining, and then also very simple 5-stage pipeline architecture. And then in chapter 5, we learned about the memory hierarchy, also memory systems. Then in chapter 6, we learned about the parallel process architecture briefly. So these are very important topics we learned in this course. Okay. But what we did not learn. So these are some advanced topics in computer architecture field. So actually, we did not learn about the out-of-order process architecture, even though the most of modern processors implement the out-of-order processing. So actually, this out-of-order processing is critical for improving the performance. Okay, but this architecture is a little bit complex compared to the very simple 5-stage pipeline architecture. So this architecture was not covered in this course. And the superscalar, branch prediction, cache coherency, and memory consistency, and then some prefetch, and then another systems like the storage systems. So these are not covered by this course. So these topics usually covered in the advanced computer architecture course. Also some courses provided in the graduate school. Okay. So if you are interested, then you can study further in these advanced topics. Okay. So those are some questions when I asked in the first class of this course, which processor is better? So you can answer why. It's a GPU and why. So I believe now you can explain. So you can explain how to measure the performance, and then actually we learned some fundamental, so basic concept in the computer architecture field. So it's a very basic actually. Okay, so but this is very essential for understanding the computer systems or computer hardware as a computer engineering or computer science student. Okay, so I'm still using this image as a COVID-19 virus image. So actually, we are passing through the very pandemic situation. The situation is getting better recently. So I hope the next semester I can provide the in-person lectures only. Okay, in the next semester, right? Okay, so you are also passing through some very hard times, difficult times actually. So because of a pandemic, but I think we are doing well. Okay. So, and then if you are interested, then you can watch this lecture video. So it's the Turing lecture provided during ISCAR 2018. So ISCAR is the very famous computer architecture conference. And then actually the Turing Award is like the Nobel Prize in computer science field or computer architecture, computer engineering field. Okay, so this is a very famous award. Okay, and then actually the authors of the textbook, David Patterson and then John Hennessy, received the Turing Award in 2018, and then they presented a lecture, and then in their lecture they mentioned the golden age for computer architecture. So which means that recently we live in the golden age for computer architecture, which means that the paradigm of the computer systems are changing because of development of software and applications. Also, we are facing some end of Moore's law, so which means that the semiconductor technology is also saturating. So the computer systems are also changing in order to support the very famous applications such as the neural networks or AI applications. So computer systems, like computer software and computer hardware, are actually connected like chains each other. So the computer software is changed, then computer hardware is also changed. And then if the computer hardware is changed, then computer software is developed based on the improvement on computer hardware. Okay, so they are developing like chains. Okay, And then recently, so we live in the golden age for computer architecture, which means that everyone, so many industries like some computer architecture, so actually computer processor industry is very critical for the economy or industries in one nation. So it's the same to the actually the semiconductor industry, but the computer processor industry is tightly coupled with the semiconductor industry. So which means that this industry is very critical. So the platform, the traditional concept of computer systems are changing recently. So that's why, so the modern ages are called another golden age for computer architecture. Okay. So I will briefly introduce about my research area. So these are my research area, like a process architecture, storage system or memory systems, or secure process architecture, and then accelerator. Okay. So these are very important topics on the computer architecture field or computer hardware. So these are critical research field. Okay. So if you are interested, then you can also work as an undergraduate intern in our lab. Okay. So also, and then I hope everyone happily take this course. Actually, I was very happy to have opportunity for teaching everyone in this course. And then so finally, so this is the last class, as last regular class of this course. And then the final class is the final exam. Okay, so I hope everyone are be prepared for the final exam. Then everyone can get good scores. Okay, in the final exam. And then also, I hope everyone can get some good grade for every courses, right? Every course, right? Okay, so thank you for your attention. Okay, and then this is the last class, and then you can see face by face on Wednesday during the final exam. Okay, thank you everyone, and then see you in the final exam. 네, 한 학기 동안 수고 많았고 감사했습니다.